Now, let's just talk about the environmental impact of some of the stuff. There are things that are radioactive all around us. We have radon in the air. We have cosmic rays that are going through you and me right now. Certain minerals in Earth are radioactive. Most of the stuff that we interact with are natural sources, and they've been there forever, and they always will be there forever. And we're not talking about lethal doses. I'll talk about the doses in a little bit. Even the coal and nuclear power plants, the fallout from weapons testing is going to be a teeny tiny bit of the radiation that we actually get to mess around with. Food and water is going to have more radiation than those guys. And more likely medicine, like x-rays and diagnostics and stuff like that, they make up about 20% of the radiation that we get. Now, let's talk about the radiation that we get from natural sources. And just want to bear in mind that I don't want to talk about the units so awful much, but just kind of pay attention to the units. First of all, lethal doses of radiation are about 500 of these things called REMs. From the cosmic sources, we get about 25. From the ground, we get 33. Air, we get lots of radiation from the air. Keep this number of 200 in the back of your head. None of these guys come anywhere near close to being lethal. Now, natural sources. Take a look at these guys right over here, and x-rays are probably the worst thing. As long as you're not out there getting an x-ray every single day, we're probably going to be okay when it comes to radioactive sources from human origins. Old school TV tubes don't use those anymore, but we don't have to worry about things like this. We're talking about very small doses for your average everyday person, as long as you're not swimming in the pools of Chernobyl or something like that. So now I want to talk a little bit more about how we can use radiation in the health professions world, and I want to, as well as in the environment, how we can do radiocarbon dating. But before I do that, I do want to talk about what a radioactive tracer is. What we can do is we can take an isotope that is radioactive, and we can put it somewhere, somehow, such that it could be ingested by a person or a plant, and we're just going to call this isotope a tracer. What's going to happen is you kind of see this purplish color. Well, the plant takes that thing in, and the plant can emit that, and then we can measure that thing using like a Geiger-Müller tube or something like that, and we can trace where this radioactive substance went through the plant. Now, there's many uses for this. Essentially, we're seeing how this thing can be ingested by whatever we're interested in. In nuclear medicine, then what we can do is we can take a radioactive substance, typically it's a gamma emitter, and we try to pair it with something that will be absorbed by a certain tissue, so you can see how it's being absorbed, and we can detect where it's coming from, and we can monitor it. That tells us where the problems are. Is this being ingested? Is it not being ingested? Is it too little, too much, or just right? And just kind of incidentally, I've heard that the whatever they pair it with tastes absolutely horrible. So, important thing is we can study internal organs without breaking out the knife. And that's a good thing. Cutting people open, it takes a while to heal from stuff like that. So, what we typically do is we choose a drug that's specific to whatever organ will absorb it, and we choose a radioactive substance like a gamma emitter, and then we can just trace the path of these things as it makes their way through the human system. In many ways, this is a good thing, and again, we're not talking about lethal doses here. We're talking about very small doses, not likely to change your lifetime by more than smoking a pack of cigarettes or something like that. Now, the last topic that I want to talk about is something called the half-life, which I kind of alluded to earlier when I showed you those simulations. And what this essentially is how long does it take for half of whatever substance that we have to decay? And typically this is like a T1/2. Sometimes you'll see it as a lambda to the 1/2, but let's do a T1/2. I think that makes more sense. Suppose we had a substance, and it had a half-life that was equal to 1620 years. It may seem like that's long, but wait until I talk about uranium. If I had a 1 kilogram chunk of this stuff, and I said that my time was equal to 0, then in 1620 years, then I'm going to have half of that left. In another 1620 years, I'm going to have half of what is right here that is left. So technically I would have half of a half. I would have a quarter of a kilogram of it. Another 16, 20 years, I'm going to have half of the quarter, I'm going to have an eighth, and so on and so forth. So that's the time that it takes for half of the quantity to decay. Now, uranium, right? This guy, uranium-90, has a very long half-life. It has a half-life of 4.5 billion years. Suppose we had a nuclear reactor and it had 100 kilograms of radioactive uranium in it. How much is left after 9 billion years? So I would say at my time 0, I would have 100 kilograms. So that might be my mass, and this might be my time. After 4.5 billion years, then I would have half that. I would have 50 kilograms. After 9 billion years, I would have half of that. I would have 25 kilograms. So I would have 25 kilograms. Now, where does the uranium go, you might ask? Well, that's a good question. Eventually it will go to lead, but bear in mind, it's going to take a very, very, very long time. And, that's kind of worrisome because all the uranium we have in radioactive plants, what do we do with that for 4.5 billion years? That's a long, long, long time. So this is kind of the path that it takes. It's actually going to take a series of alpha decays and beta decays. Remember, alpha decay is going to lower the atomic number by 2. It will change uranium to thorium. And then we might have a beta decay or 2. Maybe it's going to end up back as uranium. Alpha decay to radium, alpha decay to radon, alpha decay to polonium, beta decay, lots of paths after here. But at the end of the day, after 4.5 billion years, it's going to end up as lead. Now, we can actually detect the radiation coming off of things like uranium using a radiation detector, and it's kind of like that thing you would see, a scientist walking around with a little tube in his hand going beep, 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 beep. We have a couple of ways to do that. We have a Geiger-Müller tube, or we have a scintillation counter. This one tends to be more common, so let's talk about that. It has a tube with a gas and usually a filament in there, and the radiation is going to ionize it, turn it into a current, and you might see this thing go beep, 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 or it even makes the beeping sounds. The detectors I have in the lab even make the neat, cool little beeping sounds. Now, the last thing I want to talk about is going to be artificial transmutation, because elements can decay if we excite them. For example, suppose I had some nitrogen, and this is going to be nitrogen-14. It's going to have 7 protons and 7 neutrons. If I were to bombard this thing with some alpha particles, here's my nitrogen, there's my alpha particle, then what's going to happen is it's going to excite this thing, and it's going to cause it to decay. What's going to happen is it's going to artificially transmute it into oxygen and hydrogen. Same rules apply when we talked about alpha decay and beta decay. Over here, we have 14 plus 4, we have 28. Over here, we have 17 plus 1, we have 28. Number of protons, 7 plus 2, we have 9. Over here, 8 plus 1, we have 9. This is just artificial transmutation. And there's some important things to talk about when it comes to that. One of the things is radiometric dating. Suppose we had something like nitrogen, and if we were to bombard this nitrogen by high energy particles like neutrons in the atmosphere, then what can happen is we're going to say, well, here's our neutron, here's our nitrogen, 7 protons and 7 neutrons. Again, 14 plus 1. A little bit later, we're going to have 14 plus 1. Right here, we have 7 plus 0. Neutrons are not going to have any protons. And right here, we have 6 plus 1. Still is going to equal to 7. But what's going on is in the atmosphere, we're going to have artificial transmutation going on. We're going to produce carbon-14. It turns out that carbon-14 is a beta emitter, and it has a half-life of about 6,000 years, give or take. What it's going to do is it's going to eventually decay back to nitrogen. So you can kind of see beta emitter. We're going to lose one of the protons. It's going to, or lose one of the neutrons. It's going to turn into a proton, and out comes our electron. So this jives with everything that we would expect for beta emission. But the thing is plants continuously take in carbon dioxide. So any carbon-14 lost gets immediately replenished. Dead plants, they can't absorb this carbon-14 anymore. And that's going to be interesting because it's going to tell us a little bit about how old this thing is. What we can do is we can look at the relative amounts of carbon-12 to carbon-14, and that's going to let us date organic materials. What we can do is we can look at the radiation coming off of it, and that's going to tell us how much carbon-14 was left in it. So one thing that's interesting is suppose we had something that died about 20,000 years ago. After about 6,000 years, it's going to be emitting half of that, and then another 6,000 years, half of that, and then another 6,000 years, half of that, and another 6,000 years, about half of that. Because the half-life is going to be 5730 years, this actually gives us some limitations to carbon dating. Carbon dating is going to be good for things that didn't die yesterday, but it had to be at least 6 or 10,000 years ago. Something that died a really, really, really long time ago, well, it's not going to have very much carbon-14 left in it, and that would be very hard to measure. So carbon dating actually has some limits as to when we can date things.